Welcome back to another deep dive. Today we are not just scratching the surface, we are drilling all the way down into the bedrock of modern artificial intelligence. We're tackling a problem that sounds deceptively simple, finding things, but is actually one of the hardest, most computationally expensive challenges in computer science.
It is good to be here, and you are so right. Finding things sounds like something we solved in the 90s with, SQL databases. But we aren't talking about looking up a customer ID in a spreadsheet. We are talking about the engine that powers perception.
Right. We're talking about how a machine sees similarity. When I upload a photo to a search engine, it doesn't have a file name to look for. It has pixels. It has to find similar photos among billions of others.
Yeah.
Or, when a chatbot understands that king minus man plus woman equals queen.
Exactly. That is the world of vector search. And for a long time, doing that at scale, billion scale, was theoretically possible, but practically,
Right.
well, impossible. It was just too slow. Until the paper we are discussing today came along.
The paper is titled Efficient and Robust Approximate Nearest Neighbor Search Using Hierarchical Navigable Small World Graphs. It's by U.A. Melkov and D.A. Yeshunin. Bit of a mouthful, that title?
It is.
Let's call it HNSW.
Yes, HNSW. And it is a mouthful, but every single word in that title is earning its keep. This paper didn't just iterate on an old idea, it fundamentally changed the architecture of how we index high-dimensional data. If you use a vector database today, Pinecone, Milvus, Weaviate, even some versions of Elasticsearch under the hood, it is almost certainly running HNSW or a variant of it.
That is what I love about this. We are looking at the invisible machinery of the internet. So here is the plan for this hour. We're going to break this down into, let's say, 3 big chunks. First, the why. Why is finding the nearest neighbor so hard that we need a complex graph to do it?
Right.
Second, the what. What exactly is this small world hierarchy? And third, and most importantly, the how. We're going to dissect the methodology, the construction algorithms, the search parameters, the logic behind it to understand how it pulls off this magic trick.
The mission, if you will, is to move beyond the buzzwords. I don't want to just say it uses a graph. I want us to understand how it decides which node connects to which, and why that specific decision makes the difference between a query taking 10 milliseconds or, 10 minutes.
Okay, let's jump right in. The needle in the haystack. But it's not really a haystack, is it? Because in a haystack, you are looking for the needle. Here, we are looking for a needle that looks kind of like the needle we are holding.
That is the core distinction. We are doing nearest neighbor search. Imagine you are in a massive library. Traditional search is like looking for a book by its ISBN. You check the index, you go to the shelf, you grab it. Done.
Simple.
It's what we call O1 or O log n, complexity, easy.
But with vector search, I don't have the ISBN. I walk in and say, I'm looking for a book that feels like Catcher in the Rye, but with more aliens.
Right. And to a computer, feels like means mathematics. We represent every item, every book, image, song as a vector. A long list of numbers. Think of it like coordinates in a multidimensional space. Similarity is just the distance between those 2 points in that space. The closer they are, the more similar they are.
So the problem is, I give you a point, my query, and you have to find the 10 closest points in the entire database. Why is that hard? Computers are fast. Can't we just, measure the distance to everything and pick the winners?
We can, and that is called the naive approach, or brute force. It works perfectly. It gives you the exact 100% correct answer every time. But let's look at the math. That is linear complexity, or ON.
Meaning if I double the data, I double the time it takes.
Precisely. If you have 10,000 items, sure, brute force is fine. Modern CPUs are incredibly fast. But what if you have 100 million items? Or a billion? And you have, say, 10,000 users searching every second? You would need a supercomputer for every single user. It simply does not scale. It falls over.
Okay, so brute force is out. Dead on arrival for any real-world application. But we have solved this for other things. We use trees. That's computer science 101. Binary search trees, KD trees. You split the data in half, then half again. Why doesn't that work here?
Now we meet the villain of the story. The curse of dimensionality.
I always love that name. It sounds like an Indiana Jones movie.
It does, and it is a very real, very, very frustrating mathematical phenomenon. Trees work by partitioning space. They ask a simple question. Is the value greater than x or less than x? That works beautifully in 1 dimension, 2 dimensions, maybe even 10 dimensions. But modern vectors, like what a large language model like ChatGPT uses, are often 1024 dimensions or 4096 dimensions.
Okay, let's try to visualize that. I can't.
You can't. Nobody can. But here's the intuition. In high-dimensional space, everything is far away from everything else. The volume of the space grows so explosively that any set of data points becomes incredibly sparse. It's like having a few grains of sand scattered throughout the entire solar system.
So the idea of a neighborhood gets weird.
It breaks down. If you try to build a tree to partition that space to make those cuts, you end up with a tree where you have to visit almost every single branch to be sure you have found the closest neighbor. Your search path isn't a clean line to the answer. It's this sprawling, inefficient mess.
So the tree stops being a shortcut. It just becomes a convoluted way of doing brute force all over again.
Exactly. The structure degrades. You spend more time traversing the tree's internal structure than you would just checking the raw data points. So for high-dimensional data, trees are effectively dead.
Okay, so we can't scan everything. We can't use trees. We have to make a compromise.
And the compromise is approximation. This is the key philosophical shift. We accept that we might not find the absolute mathematical closest neighbor. Maybe we find the second closest or the fifth closest or one in the top 10. But in exchange, we want the answer in 2 milliseconds, not 2 minutes.
And for most things, that's totally fine. If I'm looking for similar shoes, I don't care if I see the 99.9% match or the 99.8% match. They're both good enough.
Right. And that brings us to the family of algorithms that HNSW belongs to, proximity graphs. The idea is, at its heart, quite simple. Instead of a tree, let's treat the data like a social network. Every data point is a person. Every person has friends, neighbors they are connected to.
Okay. So to find a target, I just start somewhere random and ask a person, hey, do you know anyone closer to this target than you are? If they say yes, I move to that friend. I just keep hopping from friend to friend until I can't get any closer.
That is greedy routing, and it works, theoretically. But there was a predecessor to this paper called the Navigable Small World Graph, or NSW. No hierarchy, just one big flat graph.
Like a flat Earth map.
Sure, that's a good way to put it. The problem with the basic NSW was that it didn't scale well enough. It had what's called polylogarithmic scaling, which is a fancy way of saying as the graph got huge, you had to take too many small hops to get across the map.
It's like trying to drive from New York to Los Angeles, but you were only allowed to use residential streets.
Perfect analogy. It would be a nightmare. You'd get there eventually, but you'd stop at a million stop signs. You'd get stuck in traffic.
You need an interstate highway.
Exactly. You need to be able to move fast when you are far away and then slow down and be more precise when you are close. And that simple idea, that need for a highway system, is the H in HNSW hierarchy.
So let's unpack that. Let's get into the methodology, section 2 of our deep dive, the high-level approach. The authors didn't just invent this hierarchy out of thin air. They borrowed from a classic beta structure called a skip list. Can we visualize a skip list?
Yes. Picture a linked list, just a chain of numbers in order. 1, 2, 3, 4, 5, all the way to a million. To find the number 900,000, you have to start at 1 and walk past the first 899,999 nodes.
Terribly slow.
Agonizingly slow. Now, imagine we build a second layer, second chain above that one. This layer only connects every 10th number, 10, 20, 30, and so on.
You can skip 9 nodes at a time.
Better, much better. Now, add a third layer. This one connects every 100th number, 100, 200, 300. Now you can really fly across the list. You find the rough area on the top layer, drop down a layer to refine, and then drop to the bottom to find the exact spot. A skip list is a probabilistic structure that lets you search a sorted list in logarithmic time O log n.
So HNSW is basically a skip list, but for a graph instead of a straight line.
That is exactly the intuition. The authors call it a hierarchical, navigable small world. Think of it like a multi-story building or maybe a set of stacked maps. Layer 0, the ground floor, contains every single data point. It's the detailed street map with every house.
Okay.
Layer 1 has fewer points. It's like a city map just showing major roads. Layer 2 has even fewer, like a state map. And the top layer might only have a handful of points. That's your globe view, showing just the continents.
So when I start a search, I don't start on the street. I start on the roof.
You start on the roof. You enter the graph at a predefined entry point on the highest layer. You take these giant steps because the points on the top layer are very sparse. They are connected over vast distances. You zoom towards the rough location of your target. Once you can't get any closer on the roof, you take the stairs down to the next floor.
And now the steps are smaller.
Right. Now you take medium steps, you refine your position, you keep dropping down layer by layer until you hit the ground floor, layer 0, where you do the final fine-tuning search among the dense local connections.
It effectively separates the zoom phase of the search from the fine detail phase.
Correct. And that structure is what guarantees that the number of hops you take is logarithmic with the size of the data set. It's extremely, extremely efficient. It's why this scales so well.
Okay, I think I get the concept. The aha moment is the stacked maps. But this is a deep dive, and I want to know how we build this thing. We don't just magically have a skyscraper of data. So let's look at section 3, the methodology of construction. When a new data point arrives, say a new picture of a cat gets uploaded to your service, how do we decide which floor it lives on? Is it based on how important the cat is or how unique it is?
No, and this is where it gets really counterintuitive. It is random.
Random. That feels wrong. Shouldn't the most important points be the express stops?
You would think so, but no. The mathematics of skip lists in these graphs show that a controlled randomness works just as well, and it's much simpler to implement. The authors use what's called an exponentially decaying probability distribution.
Okay, let's pause there. Exponentially decaying probability distribution. Translate that for us.
Think of it like a coin toss, but a weighted one. For every new element you want to add, you roll a virtual die to decide what is the maximum layer this element will exist on. The probability of getting assigned to a higher layer drops exponentially.
So everyone gets to be on layer 0, the ground floor.
Everybody's on layer 0, then we flip a coin. Heads, you get to be on layer 1 as well. We flip again. Heads, you also get to be on layer 2. The chance of making it to the top floor is very, very small.
So it's a pyramid scheme.
In terms of population density, yes. It is a pyramid. Most of the data lives on the bottom floor, and it gets exponentially sparser as you go up. And there is a crucial parameter here that the authors introduce called MLLI. It stands for the level multiplier. This parameter determines how steep that pyramid is.
And if you get that wrong,
the whole thing breaks. If MLLs is too low, you basically ban everyone from the upper floors. You end up with a flat graph again, no hierarchy, and you're back to the slow old NSW. If MLR is too high, everyone gets to go to the top floor. Then the top floor is just as crowded as the bottom floor, and you lose the benefit of the express lane.
So it's a Goldilocks problem.
It is, and what's brilliant is the authors actually derive the optimal value for n-Rs. They show that it should be 1 over the natural log of m, the number of neighbors. They tune it so that the number of hops you take remains roughly constant on average, regardless of which layer you're on.
That is fascinating. So the algorithm knows statistically how to space out the express stops on the highway. Okay, so my cat photo has rolled the dice. It won. It gets to go up to, say, layer 2. What happens next? How does it get wired in?
Now we have to insert it, and this is a really important point. The construction process is actually just a series of searches. To insert the element at layer 2, we first have to find its closest neighbors at layer 2. So we start at the top layer of the whole graph, maybe layer 5. We search for the cat photo's location. We find the closest point up there. Then we drop down to layer 4, starting our search from where we left off. Then layer 3. Then we get to layer 2.
So you use the existing graph to find the new points home.
Exactly. Once we find the closest existing points on layer 2, we draw connections. We link them. Then we drop to layer 1 and do the whole process again. Find its neighbors on layer 1, connect them, and finally we do it for layer 0. The element exists on every layer from its max assigned level all the way down to the bottom. So you are building these connections top down.
There is another parameter here that the critique listeners really wanted us to get into. The variable m, the max links per node.
Right. M is the maximum number of friends or neighbors a node can have on a given layer. The paper makes a distinction between M for the upper layers and M max 0 for the ground layer. Usually you want the ground layer to be denser to have more connections because that is where you need the highest precision.
And what happens if m is too small?
If M is too small, the graph might get disconnected. You might have islands of data with no bridges between them. You can't get from A to B.
Oh.
If M is too big, you use a ton of memory storing all those links, and just checking all your neighbors at every step starts to get slow. So again, it's a trade-off.
So m is the friendship limit. If I already have m friends and a new, better friend comes along, what happens?
You have to dump one of your old friends. The algorithm is dynamic. It will prune the connection to the farthest neighbor in your current friend list to make room for the new, closer one. It's constantly rewiring itself to keep the best connections.
This brings us to section 4, the search process itself. We have built the graph. Now a user comes along with a query. We talked about greedy search. I move to the neighbor that's closest to my target. But greedy can get you stuck, right? What if I'm at a local minimum? I'm standing on a small hill and every step I could take is down. But the real Mount Everest is across the valley.
That is the classic problem with any kind of greedy routing or gradient descent. You get stuck in a local optimum. And to fight this, HNSW introduces a really important parameter called F. It stands for expansion factor. Specifically, there is F construction, which is used when you're building the graph, and F search, which is used when you're querying. They can be different.
So how does F solve that local minimum problem? What is it actually doing?
Instead of just keeping track of the one current best node, the single closest point found so far, the algorithm maintains a priority queue list of the top F candidates it has seen during the search. Let's say I search a set to 100.
Okay.
I'm at a node. I look at all its neighbors. I don't just pick the single best one and jump. I evaluate all of them. I add them to my candidate list. My list might now have, say, 110 candidates. I sort it by distance to the query, and I throw away the worst 10, keeping only the top 100. Then I take the best candidate from that list that I haven't visited yet, and I move there.
Ah, I see. So it allows the algorithm to explore promising directions, even if the immediate next step isn't a perfect improvement. It acts as a buffer, or like a wide search beam.
That's a great way to put it. It's a wide beam. It expands the search radius at each step. It's like searching a house for something. Instead of walking strictly toward the smell of cookies, you search the whole room you are in thoroughly before moving to the next room that smells even more like cookies.
And I assume this is a tunable knob.
It is the main knob you turn to balance speed and accuracy. If you increase F, you search more thoroughly. Your chance of finding the true nearest neighbor, what we call recall, goes way up. But obviously it takes more computational power. You're doing more distance calculations. If you decrease F, it's much faster, but you have a higher chance of getting stuck in a local minimum and missing the best possible target. It gives the user direct control over that trade-off.
I want to push back on this a little bit. You're maintaining a priority queue of, say, 100 or 200 items, and you're constantly adding to it, resorting it at every hop. Doesn't that overhead just eat up all the speed gains?
That is a very sharp observation. And yes, managing that queue is computationally expensive. It's not free. However, you have to remember the alternative. The alternative is calculating the distance to millions or billions of points. The single most expensive operation here is the distance calculation itself, especially between two, say, 1,000 dimensional vectors. That's a lot of floating point math. Managing a sorted list of a few hundred integers, which are just the IDs of the nodes, is cheap in comparison. So even with that queue overhead, we are winning by orders of magnitude because we are dramatically minimizing the number of those expensive distance calculations.
Fair enough. Okay, so now we arrive at what I think is the most technical and maybe the most innovative part of this paper. Section 5, the secret sauce of neighbor selection. We mentioned earlier that when you connect a point to its neighbors, you don't just pick the closest ones. And I have to ask again, why not? Isn't this nearest neighbor search? Why wouldn't I want my connections to be with my actual nearest neighbors?
This is the heuristic. And this is the part that, in my opinion, makes HNSW so much more robust than other proximity graphs. If you just pick the M closest points, you run into a huge problem with clustering, which is common in real-world data. Imagine your data isn't uniformly spread out. It has clumps. You're trying to insert a point into a very dense cluster.
Okay.
Your 5 closest neighbors are all basically standing on your toes. They are all in the same direction from you. If you connect to them, you are highly connected locally, but you have no links pointing out of the cluster. You are trapped in a bubble.
It's an echo chamber. You only have friends who are exactly like you and live next door.
Exactly. You need diversity. You need some long-range links that can act as bridges to get you to other parts of the graph. To achieve this, the authors use a clever heuristic that approximates what's called a relative neighborhood graph.
Okay, let's break that down.
Here is the logic, and this is the love triangle logic you might have heard about. Let's say we are inserting point A. We are considering connecting it to a candidate, point B. The algorithm asks a simple question first. Is B one of the closest points to A we've found so far? If yes, it's a candidate.
Okay, standard.
But UT, then it does a second check. It looks at all of A's already established connections. Let's pick one and call it point C. The algorithm then asks, is B closer to C than it is to A? If the distance from B to C is smaller than the distance from B to A, we throw B away as a candidate for A.
Wait, walk me through that again. B is a good candidate. It's close to A, but we throw it away just because it happens to be even closer to C, one of my other friends.
Exactly. Because if B is super close to C and A is already connected to C, then A doesn't really need a direct link to B. A can just go through C to get to B. That hop is very short.
The connection A to B is redundant.
It's redundant. It's a waste of a precious connection slot. By rejecting B, the algorithm forces A to look for a neighbor in a different direction, even if that neighbor is slightly further away in absolute terms.
Wow. Okay, I see it now. It prioritizes unique directions over pure proximity. It's building a network for travel, not just for local chit-chat.
Yes. It enforces a wide field of view. If you look at Figure 2 in the paper, it shows this visually. It's a fantastic diagram. The standard method, just picking the closest, creates these tight little clumps, these isolated communities. The heuristic method creates this beautiful web that looks like a triangulation. It actively builds bridges across the empty spaces in the data.
And why does this matter so much in practice?
Because real-world data is nasty. It's not clean. It's clustered. It has voids. It has disconnected islands. Without this heuristic, the greedy search would find the first cluster and get stuck in it, thinking it had found the best answer. With the heuristic, the graph maintains global connectivity. It gives you a much, much higher probability that you can get from anywhere to anywhere else efficiently.
That is genuinely clever. It's maximizing the information density of each and every connection in the graph.
Correct. It's making every single link count.
Let's move to section 6. Assumptions and comparisons. Every model, every algorithm assumes something about the world. What does HNSW assume?
Well, the biggest assumption is that you're operating in what's called a metric space. This means that the distance function you're using obeys the triangle inequality. Basically, the shortest distance between 2 points is a straight line. If A is close to B and B is close to C, then A should be at least somewhat close to C.
And if it's not?
If you have a weird non-metric data set where distance measurements don't follow that logic, like A is similar to B, B is similar to C, but A is the complete opposite of C, HNSW will struggle. Its greedy navigation will get confused.
But for standard things, cosine similarity for text, Euclidean distance for images, that holds up.
Yes, for 99% of use cases, it holds up perfectly. The second, more subtle assumption is that the random level assignment will statistically produce a balanced hierarchy. They can't prove it works perfectly in every possible theoretical edge case, but in practice, the law of large numbers ensures it works incredibly well.
How does this compare to the competition? We've talked of trees being bad for high dimensions. What about other popular methods like product quantization or inverted file systems, often called IVF? Those are huge in the industry, specifically in libraries like Face from Meta.
This is the big trade-off discussion. It really comes down to memory versus speed. HNSW is a graph. Graphs take up space. You have to store all those links, all those pointers from one node to its neighbors in memory. In RAM, if you have a billion vectors and each has 32 links, that is a lot of pointers. So HNSW is memory hungry.
Okay, and product quantization.
Product quantization, or PQ, is fundamentally a compression technique. It takes your big, high-precision floating point vectors and squashes them down into tiny, low-precision codes. This means you can fit way, way more data into the same amount of RAM.
So PQ is much more efficient on space.
Dramatically so.
Right.
But that compression is lossy. You lose accuracy, you lose precision. And generally speaking, for a given accuracy target, HNSW is faster in terms of raw queries per second. So the choice for an engineer is usually, if you have a ton of RAM and you want the absolute fastest, most accurate search possible, use HNSW. If you are trying to squeeze a massive data set onto a small server and you can tolerate slightly worse results and slightly slower queries, use PQ or IVF.
Or, as many state-of-the-art systems do now, combine them. Use HNSW as the coarse index to find the right neighborhood, and then use PQ on the vectors themselves to save space.
Exactly. Hybrid approaches are very common and often give you the best of both worlds.
All right, section 7, performance. We talked a lot about search speed. What about construction speed? If I have a new batch of 1 million images to add to my index every night, does it take 10 hours to build?
This is another huge win for HNSW. Because it's a graph and insertions are fundamentally local operations, the construction is what we call embarrassingly parallel. You can use all 64 cores of your server at once. Each core can grab a data point from the queue, traverse the graph, and then it only needs to lock a tiny local neighborhood of the graph to add the new links. The paper shows that construction speed scales almost linearly with the number of CPU cores you throw at it.
So it's fast to build, fast to search. What about the robustness? The title specifically says efficient and robust.
Right. Robust here means it doesn't break when you change the data type. It's not brittle. Some algorithms are very finely tuned for, say, text vectors, and they perform poorly on image vectors. The authors tested HNSW on a whole bunch of different data sets. SIFT, which are image features, GLOVE, which are word vectors, MNIST, which are handwritten digits, and even just random uniform data. And it performed at or near the top of the chart for all of them without needing major parameter retuning. That is very, very rare.
It really is the Swiss Army knife of approximate nearest neighbor search. Okay, we're nearing the end of our hour. I want to try and synthesize this. Let me see if I have this right. We have taken a massive billion-item haystack. We built a probabilistic skyscraper where some items randomly get to be express elevators. We connected them using a clever love triangle logic that forces diversity and prevents getting trapped in local clusters. And we search it by parachuting onto the roof, sliding down floor by floor, and keeping a wide beam of candidates to make sure we don't miss our target.
That is a very colorful but a surprisingly accurate summary. Yes.
So why does this matter to the listener? Why should they care about the guts of this, about parameters like $9 and EVF?
Because we are moving rapidly into an age of retrieval augmented generation (RGA) and massive context windows for AI. When you ask an AI a question about your company's entire 10-year history of documents, it isn't reading all 10 million documents in real time. That's impossible. It is using an algorithm like HNSW to find the 5 most relevant documents in milliseconds, and then it reads just those 5. HNSW is the bridge between the world of static data and the world of active intelligence. It is the bottleneck. The better this algorithm gets, the smarter and faster our AI assistants become.
It effectively gives the AI a long-term memory that is both functionally infinite and instantly accessible.
Yes. It solves the latency problem of knowledge retrieval.
I want to leave the listener with one final thought, our provocative thought. The authors mention in their related work section that these navigable small world networks appear everywhere in nature. Social networks, sure, the 6 degrees of separation, but also biological neural networks, the human brain.
That is the most intriguing part to me. The brain doesn't have a hash map. It doesn't run on a B tree. But it does have neurons connected by synapses, forming this massive, intricate graph. And we know the brain is a small world network you can navigate from the concept of Apple to Steve Jobs to computers in just a few mental hops. It is very, very likely that evolution, through trial and error over millions of years, stumbled upon a structure that is conceptually very similar to HNSW for efficient information retrieval.
So by engineering this hierarchical, navigable small world to make our computers more efficient,
we might just be reverse engineering the indexing system of our own minds. We are, in a way, discovering the fundamental geometry of what it means to have an efficient memory.
that is a thought that makes all the O-log and math feel a lot more poetic. We have unpacked the layers, we have walked the graph, and we have found our nearest neighbor. Thank you for guiding us through this high-dimensional space today.
My pleasure. It is always good to explore the map.
And thank you to you, the listener. Keep exploring, keep questioning, and we will see you on the next deep dive.